Okay. Excellent. So our first speaker this morning is Łukasz from AGH in Krakow. He is a PhD student from Piotr Oprocha, and he will speak on dynamics of Lorenz maps, renormalizations, and invariants.
Thank you. And I would like to thank the organizers for the opportunity to give a talk today. So, okay. So the talk is based on joint work with Piotr Oprocha, renormalization in Lorenz maps, completely invariant sets, and periodic orbits. And the presentation plan is as follows. At first, I will give a basic definitions, especially what is Lorenz map and its renormalization. Then I will discuss the main motivation for our work, that is the theorem of Yiming that tried to connect renormalizations with completely invariant sets. As you will see, some of his statements are incorrect, so I will present appropriate counterexamples, and then I will present our attempt to improve his statements in some special case, that is in case of expanding Lorenz maps with so-called primary Enka cycles, that is some special periodic orbits. And at the end, I will present some open questions related to this topic. Okay, so the main object in our considerations are expanding Lorenz maps, that is interval maps satisfying the following three conditions. At first, there is a critical point C such that the map is continuous and strictly increasing on both intervals 0C and C1. There are left-sided and right-sided limits at point C equal to 1 and 0 respectively. And the last condition is the reason why we call these maps expanding. So it says that f is differentiable with slope greater than 1 everywhere except at most a finite set. Okay, so note that this last condition implies that the set of all pre-images of critical point C is dense in 0, 1. And these conditions, this density sometimes is used in the definition of expanding Lorenz map instead of this stronger condition about derivative.
Do you assume something about derivatives at the point C left side for the branching?
No.
No, because I think I remember from Lorenz model plus minus.
In this case, we only want to have differentiable map everywhere except at most the finite set. Okay, but we assume that the image of critical point is always equal to 0 or equal to 1. Okay, a few words about motivation, why people study these maps. Sorry?
The critical point of the breakpoint.
Yes. So these maps appear as Poincaré maps in geometric models of Lorenz attractor. Here we have some fundamental papers on this topic. Moreover, expanding Lorenz maps with constant slope, so-called beta transformations, are important in number theory, especially in expansions of real numbers in non-integer bases. And in addition, Lorenz maps are also important in fractal geometry. In particular, they appear in recent works of Barnsley. Okay, now I will give you a definition of renormalization of Lorenz map. So assume that we have expanding Lorenz map F, and if there is a proper subinterval UV containing the critical point C, and there are integers L and R both greater than 1, such that the map G, defined in this way, is itself a Lorenz map after a proper rescaling, then we say that F is renormalizable, or that G is a renormalization of F. And we write shortly, G is equal to F to the L, F to the R. In this case, the interval UV is called renormalization interval. Here, F to the L means the composition of the map F with itself L times, and similarly for F to the R. So renormalization is some return map of original map F to some smaller interval around a critical point C. I will show you an example. So consider a piecewise affine expanding Lorenz map T, defined by this formula and these values of beta and alpha. Then the critical point has this value, okay, and denote the points from by pi, denote by pi the points from trajectory of 0, and by qi the points from trajectory of 1. Let's see the graph. Okay, so here is a critical point C, this red dot, and we also have some fragments of trajectories of 0 and 1.
Ah, so it is also example of Lorenz.
This is the example of Lorenz.
Ah, okay, so because I had some. Okay.
Yeah, I will show. Yeah, I will show that this map is renormalizable. So, okay. So at first, consider this gray interval around critical point. I will show you that we have a renormalization defined on this interval. So look at this orange part, so interval P1C. After first iteration, it goes to the right, then it goes here to the left, after second iteration, and after third iteration, it is again contained in this gray interval Q1, Q2. So it returns after 3 iterations, and it does not cover the critical point before that. Okay.
Do you assume in this renormalization, or maybe it follows from other properties, that these intervals, images, let's right, pieces, that they are all disjoint each other before they fit?
No.
Don't, so they don't. No. Or they cannot capture critical points. Have them more than one critical. Maybe they are all different.
I'm not sure, because
But you assume that there is only one critical point.
Yeah, but if I hit critical points, so my intervals can split into two intervals.
Both can.
Yeah, and
So you enroll them.
so, okay.
Can you show again? So you start, where do you start, the gray interval? So what I'm supposed to be looking at?
I want to show you that I will have renormalization on this gray interval.
Okay.
So-
we look at the interval from P1 to.
P1 to critical point C. Okay. It goes to the right, then it goes to the left, and it is,
Second side.
yeah.
And where does it start? It starts at the critical point, or it starts at? Because it's hard to see from here.
Oh, yeah. Yeah, it is. One more time. Yeah.
Three, oh,
Yeah, it is P4 Q2. So after third iteration, it contains critical point, but it's okay. It is okay.
Then map has only one critical point.
Yes.
Is already.
Yes.
My question is, they don't have on the way going back, don't hit again. Point, because you assume there is only one critical point.
Yes.
From the conclusion.
Mhm.
But it doesn't answer my question whether they can overlap.
Mhm.
The same may be not necessary.
so in this case here, well, but did you want to overlap? For the next interval, there's going to be some overlapping of the. Yeah, I think so. Okay, let's see what's gonna happen.
Okay. So now consider the second one. The interval C Q2. So it goes to the left, and after second iteration, it is contained in this gray interval. Okay, so
See, so for the complex situation, dynamics, the jointness of those are simple, primitive. Otherwise, they can mismatch.
okay. So here we will have a renormalization G defined on this interval. Okay, and after rescaling the domain, I will again have expanding Lorenz map of 0, 1. So the graph of the map G after rescaling is this blue one, and the original map T is the gray one. Okay. And we have simple observation that if I have renormalization f to the L, f to the R defined on interval UV, then this interval UV must be equal to this one. Okay, where I have one-sided limits at critical point C. It follows from the definition of Lorenz map. Okay, so there are many connections between renormalizations and other dynamical properties, like, for example, transitivity. They are nice results connecting renormalizations with alpha limit sets. And in particular, Yiming in his paper Renormalization and Alpha Limit Set for Expanding Lorenz Maps claimed that there is a one-to-one correspondence between completely invariant sets and renormalizations. So first I will give a definition. A non-empty set E is said to be completely invariant under F if it is equal to its image and pre-image. Okay. And for any open and non-empty set U, by n of u, we denote the smallest integer n such that f to the n of this set u contains the critical point. So the main result from Ding's paper says that if I have completely invariant closed and proper set E, then I can construct a renormalization using a following procedure. At first, I compute E minus E plus, that is 2 points from the set E that are the closest to the critical point C, from the left and from the right. Then I compute L and R. So I look at the first iteration when this interval E minus C covers the critical point C, and the same for this one. Okay? And then it turns out that point E minus is L periodic and E plus is R periodic. And moreover, the following formula gives us a renormalization of map F. Okay. And the second part of this theorem says that, on the other hand, if I have a renormalization G, then I can find a unique, proper, completely invariant closed set JG such that if I use this set in the procedure from the first part of Ding's theorem, then I will obtain the renormalization G. Okay, so I have one-to-one correspondence between completely invariant and proper and closed subsets and renormalizations. So the idea of the second part of Ding theorem says that at first assume that I have renormalization G, okay, defined on some interval UV. Then Ding says take the set of all points whose trajectory intersects this open interval UV. Next, Ding claims that this set Fg is a proper, completely invariant open set. So its complement will be closed set and also proper, completely invariant. And if I use this set in the procedure from the first part of Ding's theorem, then I will obtain the renormalization G. But it turns out that it may happen that the set JG is empty or not completely invariant. Okay, and I will show you.
J from Julia and F.
I don't know. I will show you two examples. So the first one is again the map T1. So
just to clarify, so the first part of Ding's theorem is correct. It's the second part that has a problem.
There are some technical issues. For sure, it is correct when E is a proper subset of 0, C, C1. It cannot contain critical point C because then it will be the whole interval. And there is also some problem when it contains 0 or 1. Oh, for example, if the 1 is fixed point, then the singleton 1 will be completely invariant, but it does not give you any renormalization. So if the set E is subset of this one, then the first part of this theorem is okay. Okay?
So as stated, everything is wrong.
Sorry?
So as stated, everything is wrong.
One of them.
As stated,
Yes. Oh, yes, yes. But yeah, but the idea is nice. Okay. So I have this map given by these values of beta and alpha, and I have renormalization G that I discussed at the beginning. So it's the renormalization defined on this gray interval P1, Q2. And we can observe that all points from interval 0, 1 eventually falls into the interior of this interval P1, Q2. So this orange one, after one iteration, is contained in renormalization interval, and this orange interval first goes to the left, and after the second iteration, it is also contained in this gray interval. Okay, and the endpoints P1, Q2 also fall into the interior of this interval. So in this situation, the set JG is empty. Okay? And in fact, there is no proper closed and completely invariant set that defines the renormalization G. And the second counterexample, consider the expanding Lorenz map defined by this formula. Then the critical point is 1/2. Denoted by U the image of point 0 and by V the image of point 1. So here we have a graph of this map T2 and the graph of its composition with itself. So we can observe that on this interval UV we also have renormalization. There is a renormalization defined on this interval. And now observe that the only points that never fall into the interior of this interval are 0, U, V, and 1. Okay? But 0 and 1 and 0 and 1 don't belong to the image of set JG. Okay?
so this one, can you go back? So J is, what is F? G? I forgot definition.
F.
J are points which
Uh,
don't.
Yeah, set of points that set of points whose trajectories never intersect the open interval UV.
J. Points which.
JG.
J is just UV which never intersect.
Yeah, set of points that never.
So what is F? F was complementary to
Yeah.
J, or
Yeah.
so F is our points that fit.
Yes. Yes.
Right?
FG is the set of points that.
And these are kind of outside. Usually there is a normalization in complex case and then this is the normalization. Something that is invariant set outside, which like counter or hyperbolic. Not completely. We are. Nevertheless. Okay.
Okay, so this part of Ding's theorem is incorrect. And the question is, which renormalization can be obtained from the procedure described in the Ding's theorem? In particular, when the set JG is non-empty and completely invariant. Okay, so at first I will give an answer on the question when it is completely invariant. So look again at this.
So that's the theory of renormalization. Inspect of the composition with respect to the quite a melon. Trees here and personal continue solenoid.
But they don't deal with this kid. They don't deal with discontinuous math.
No, I mean, continuous. You usually say about C2. Maybe something a little more general. Here, we don't make spectrum. Will you continue renormalizations until solenoid instance renormalizable, or you are just classing one?
I cannot have infinitely many renormalizable map because of this stronger expanding.
So you say it can happen?
Yeah. It can happen if you have this weaker condition, not the one about derivative, but the second one.
No, I believe it. Solenoids, so much of tensor power. There's no expanding there. Kind of parabolic.
Okay. Look again what happened in this example. So the image of critical point is 0. So the pre-image of 0 is a singleton, and clearly the point C does not belong to set JG. And since the image of critical point is 0, the pre-image of point 1 is empty. Okay, so both points 0 and 1 cannot belong to the image of set JG. And it turns out that 0 and 1 are the only problematic points. So in general situation, if I have expanding Lorenz map F and I have some renormalization defined on interval UV, then we proved with Piotr that then if the set JG is non-empty, then it is completely invariant if and only if the trajectory of U and V does not intersect the open interval UV. Okay, so in this case, the points 0 and 1 cannot belong to set JG, and then everything is fine. It is completely invariant. Okay. But still, this set can be empty. And to answer the question when it is non-empty, we use the notion of primary NK cycles. As far as I know, this notion was introduced, at least in this form, was introduced by Yiming, and the periodic orbit of period n is NK cycle if we can order at its points as follows. Additionally, they behave in such a way that after each iteration, the index increases by k, and I take the remainder from dividing it by n. And the second thing, the integers k and n are coprime, and the image of 0 and 1 satisfy these inequalities, then we say that the NK cycle is primary. Okay, I will show you an example. So it is again our map T1. Here we have points Z0, Z1, Z2, Z3, and Z4. And point Z0 goes to Z2, Z2 goes to Z4, Z4 goes to Z1, Z1 goes to Z3, and Z3 goes to Z0. And moreover, the image of 0 and image of 1 are between points Z1 and Z2. So indeed, this map has a primary 5-2 cycle.
Can you explain what is not primary? So what would not be primary?
Just NK cycle?
Yeah, some cycle that doesn't satisfy the property. I didn't quite follow the property.
So I have just a periodic orbit with points that I can order it in this way. So
can I show you the rest of the definition? I didn't quite follow. So so they're permuted according to they're permuted. If you add on the right, then you need to jump. Jump.
You are on the right, then okay, because on the right, you are on the indices.
yeah, if I'm on the left, then I need to go. Yeah.
We want to read the last definition. 0.3 is looking at this one.
Sorry.
I don't quite understand. Maybe this is something. What does it give you?
You will see. You will see soon. Okay.
So to clarify, so here Z1 is image of Z0, Z2 is image of Z1.
No.
This is geometric order, dynamical jumping.
Yeah.
Each
Z0 goes to ZK. Yeah, ZK modulo n, so ZK.
But you don't like that the J equal to Fj of Z0 is the
Sorry. Yeah, nothing. Sorry. It's not true. So maybe again, example. So here we have 5-2 cycle. So Z0 goes to Z2 modulo 5, so Z2.
Oh, I see. And then to Z4, and then must jump again. Z4 must jump again. Z1.
Z0 goes to Z2. Okay. Then Z2 goes to Z4.
And immediately must jump back.
Then Z4 goes to Z1.
Is there a way to move it?
Z1 goes to Z3.
And again jumps back.
Yeah.
It's actually to rotation. It's by itself.
Okay. And the images of 0 and 1 are between Z1 and Z2. Okay. So a few words about properties of the maps with NK cycles. So at first consider the case of the map with 2-1 cycle. Okay. And consider the interval Z0 and 1. After one iteration, this interval splits into two intervals where the green part goes to the left, so C Z1 goes to 0, Z0. And the orange part goes to the right to Z0C, Z0C goes to the Z1, 1. And after second iteration, the green part is again contained in Z0, Z1. And the orange part also is contained in Z0, Z1. Okay, so after 2 iterations, this interval come back to interval 0, 1, Z0, 0, 1, Z0, Z1. Okay, so if I take any point from here, from this interval around critical point, I need exactly 2 iterations to come back. Okay, and what else is important, that the images of this interval cover the whole interval 0, 1, except 1 point 0 or 1, depending on what is the image of critical point C. Okay, and in general case, if I have NK cycle, again, consider this interval around critical point C, then the green part goes to the left, the orange part goes to the right, and after second iteration, there are contained in ZK minus 1, ZK, okay? So that is why I want to have these inequalities, okay? And I need to have another n minus 2 iterations to come back to this interval around critical point. And again, the images of this interval around critical point covers the whole interval 0, 1, except 1 point. Okay, so using these properties of maps with primary NK cycles, we were able to prove our theorem. So assume that we have expanding Lorenz map with a primary NK cycle, then the following conditions hold. At first, I always have a renormalization f to the n defined on this interval, which is contained in this one. Okay, I always have this renormalization. The second thing is that if I have any other renormalization, f to the L, f to the R, and at least one of the numbers L and R is greater or equal to n, then n divides both L and R. But still, it may happen that both of these numbers are less than n. Okay? And the set JG contains the NK cycle, always. And JG is the set JG, which is related to this renormalization f to the n, okay? I have this quality. So in fact, these points from NK cycle are exactly the same points that are exactly the same points as E minus and E plus from Ding's theorem. Okay. And moreover, if image of 0 and image of 1 satisfy these conditions, or at least one of these conditions is satisfied, then the set JG is not completely invariant. But if I have these conditions, then the set JG is completely invariant and proper subset of 0C, C1. Okay, so this is nice thing. I can use this set in the procedure from Ding's theorem and obtain the renormalization G, that is F to the N, F to the N. Okay, and it turns out that in the situation from here, that is when the set JG is not completely invariant, I still can use it in the procedure from Ding's theorem and successfully obtain the renormalization G. Okay, it is not completely invariant, but it is non-empty. I can use it and obtain this renormalization. Okay, so now let's focus on this part. So, as I said, it may happen that both these numbers are less than n, and we have such an example. It's again our map T1. As we discussed, this map has 5-2 cycle, so for sure it has renormalization F T to the 5, T to the 5, but we also have this renormalization that we discussed at the beginning. Okay. So, in general case, when I have expanding Lorenz map with a primary NK cycle, and if I have some renormalization F to the L, F to the R, then by our theorem, we can have two cases. The first one is that both numbers L and R are less than N, and the second case is both are divided by N divides both of these numbers, L and R. Okay, so in the first cases, when both numbers are less than N, then I will have these inequalities. It is because, as I said, when I take point from this interval around critical point, I need N iterations to come back. Okay, but if L and R are less than N, it must happen that P is less than this one and Q is greater than this one. Okay, so in this case, this interval is contained in the complement of J, G, so in this set F, G. And therefore the set JG is empty because, as I said, the images of this interval cover the whole interval 0, 1. And if I have the second case, then when N divides L and R, then by the same argument, P and Q belong to this interval around critical point. So in this case, the NK cycle is contained in the set JG. So this set, in this case, is non-empty. Okay. So now I want to very quickly give you some idea how big is the class of expanding Lorenz maps that satisfy assumptions of our theorem. So I will focus on expanding Lorenz maps with constant slope, so-called beta transformations. So denote by delta the set of parameters B and A, okay, and consider an expanding Lorenz map with constant slope. The question is, for which parameters beta alpha, this beta transformation has a primary NK cycle. And I will use the computations from the paper of Oprocha, Potorsky, and Wright. they described the set of parameters when the beta transformations has n1 cycle and n minus 1 cycle, primary, of course. Okay, so let n be an integer greater or equal to 2, and let beta be in this interval. If alpha satisfies these strange inequalities, then the beta transformation has a primary n1 cycle. And moreover, if alpha is equal to this one or to this one, then the image of 0 is z0 or image of 1 is z1. And we also have, in some sense, a symmetric case. So if alpha satisfies these inequalities, then I have n minus 1 cycle, primary. And moreover, if alpha is equal to this value or this value, then the image of 0 is equal to zn minus 2, or image of 1 is equal to zn minus 1. Okay, so I will show you a graph. So here we have our parameter space, and okay, this curve is given by this formula. This curve is given by this formula. So for parameters which belongs to the blue area, we have primary 2-1 cycle. Here we have primary 3-2 cycle and primary 3-1 cycle, and so on, so on. Okay, 10 is enough. So for parameters from these blue areas, we have n1 cycle, primary n1 cycle, or primary n minus 1 cycle. And in the parameters from the border, we have these conditions. Okay, so if I take beta transformations defined by values from the border, then the set JG is not completely invariant. So for these parameters, we have counterexamples to Ding's theorem. Okay, and here we have also these maps, and they are also interesting because for these red parameters, I have renormalizable and transitive maps. Okay, and the last thing, we have example of Lorenz map with primary 2-1 cycle and 3 renormalizations. This one is for sure because we have our theorem, and we also found this one and this one. And it turns out that the set JG related to these renormalizations, the sets JG related to these renormalizations are equal. All are equal, and if I use it in the procedure from Ding's theorem, I can only obtain this one. So it suggests that the most problematic renormalizations are these where the L and R are not equal.
Łukasz, excuse me, I think you need to wrap it up now.
Okay, yeah. So only 2 questions. It is even possible to obtain this renormalization, such renormalization with different numbers L and R using the procedure from Ding's theorem, because we don't have such an example. And the second one, if I have such a renormalization when L is equal to R, so in this case, maybe the set JG is always non-empty, and even it is not completely invariant, maybe I will always use it in the procedure from Ding's theorem and obtain renormalization. Okay, some references. Thank you.
We have one very quick question. Of course, many questions can be asked afterwards in the conversation with Łukasz.
Is there like a renormalization theory that starts here that maybe leads to, for example, well, I mean, like you said, in this uniformly expanding situation, it's not possible to do infinitely many renormalizations. So is your discussion very sensitive? That group, does it really require that it be uniformly expanding?
Okay, so most of our results, remain true if we assume this condition instead of this one. Okay, but probably our main theorem that I showed does not need this condition. This one is enough, but I'm not sure at this moment. I need to check it, but mostly we use this condition.
If you go to this picture of the parameter space, so yeah, you plotted the n minus 1 and 1 cycles. Yeah. So if you consider the other n and k, you get a Fourier tree structure like in the rationals. For instance, you consider maybe 1, 2 and 1, 3. These are two of your links. But then in between, you can consider maybe 2, 5, and that should give you probably
Yes. There are for another NK cycles, we have another regions here.
But are they parallel to these?
Are they joint quests?
Yeah, they should be disjoint. Yeah, they should be disjoint. They look very similar to this. Okay. Probably you can find it in the PhD thesis of Paweł Potorski.
And are they ordered like Fourier functions?
I don't remember now.
Seems
Let's bring our speaker again. You can start the next joining us. Yeah. Okay.